Okay, can you hear me now?
Yes.
Okay. Yeah. So yeah, today we'll talk about a particular tool, which is called Quantum Fourier Transform. Okay, it's just like so QFT. This is just like the analog of DFT, the Discrete Fourier Transform. Uh, yeah, and this technique, this tool. So I'll give you a circuit representation of this one, this transform, and so that circuit will ultimately can be realized by a unitary matrix, just like DFT, and this can be applied on n qubits. Okay, so I'll talk about that. There's quantum Fourier transform, but before that, um, before defining this quantum Fourier transform, we'll talk about a very special matrix, unitary matrix, which will be used to implement this. And so this is special gate also, you can say, which will be used to implement this quantum Fourier transform. And that special gate is something called permutation or quantum permutation. So, but this is also very special kind of permutation. So, quantum permutation. So, quantum permutation is, it is nothing but a relation of a permutation matrix. But here, since it can have, so the input can be in qubits, so the dimension of the matrix will be of order. So here, the corresponding unitary matrix or the permutation matrix U, okay, which has to be of dimension to the power. So this has to be dimension to the power n times 2 to the power n. So this is a 2 to the power n by 2 to the power n dimensional matrix. So, and how many such matrices can be there? Permutation matrices. So this will be 2 to the power n factorial. So this many permutation matrix can be there of order 2 to the power n by 2 to the power n. But I'll talk about one particular permutation which will be used in order to realize QFT, quantum Fourier transform. And that permutation, well, let's say, we'll denote it as P. So what it does is, so if you have a so if the input is okay, so if the input is like, okay, so okay, let me write it this way. If the input is, let's say, some let's say some k1, k2, kn, so then if we apply that, if this is the input, then output will be kn minus 1 dot k1. So it will reverse the qubit states. So this the ki's are nothing but 0, 1. So there are n qubits, and here there are n qubits. So it will just reverse the order. So let's say if we apply this matrix P or this gate, then it will reverse. So sometimes it will also called reversal permutation. So this P is also called reversal permutation. Okay, so for example, If I give you some examples, so how to check this? So basically what happens is you take all the basis vectors here, okay, so like c to the power 2 and all, take all the basis vectors here, okay, and then all these basis vectors can be written as this k1 k2. So this is basically k1 times k2 k times dot times kn. So we take all these basis vectors, ki is at 0 or 1, then it should change reverse the order of the qubits. So it will be kn times dot times k1. So if n equal to 1, so I'm just giving you the examples how this permutation will look like. So if n equal to 1, then the matrix should be, so let me write it as 2 to the power 1. So instead of p, if I write 2 to the power n, to understand what is the size of the order of this matrix. So p 2 to the power 1, this will be 1 0 0 on the identity matrix, because there is just one qubit here, so it will keep it invariant, so there is no reverse. Now if you take n equal to 2, it will be, let me write it as p to the power 2. So you can check that this will be 1 0 0 0 0 0 1 0 0 1 0 0 0 0 0 1. And if n equal to 3, so this will be a huge matrix. So this will be 8 by 8 order matrix, and so this will be okay. So before before writing it down, so how do I construct such matrix? What should be the entries also of the ijth entries, okay, of this matrix p to the power n? Okay, so basically what is happening, what we are saying here, that if so original definition of this pn is like ki is like from 0 1. So if you take the basis states, then it reverses the order. But in general, this is a general purpose. The purpose is like it could need not be the basis states. Okay, it could be corresponding to any basis. This is the ki is in 0 1. This is a standard basis. Okay, but in general, it should be like, in general, the definition actually should be p to the power n. If you take that, and if you take, let's say here, psi 1, psi 2, dot, let's say some psi n, then it should give us psi n, psi n minus 1, dot psi 1. So it should reverse the order. Okay, now if I want to look at this, like suppose I want to construct what is the structure of this matrix. So this is a very special matrix. The single matrix will be a very special matrix. So in order to understand this reversal matrix, okay, what should be the property of this kind of unitary matrix? So first of all, it should be like all the entries should be 0 1 1. Okay, because it is after all a permutation, and definition of a permutation matrix is the non-zero, the entries of this matrix should be 0 or 1, and there should be at most, or maybe we can say like there is exactly one non-zero entry in each row and each column, and that entry has to be 1. So that has to be the permutation matrix. Okay, now, so what we are trying to say here, that p to the power n, let's say k1 k2 kn, we'll come back to this, like it should also transfer, I mean it should also reverse all possible qubits. It need not be just the standard basis, but if it can do it for standard basis, that is enough. So what we are saying here is k1 k2 kn, this would be equal to kn1 kn minus 1 dot k1. So that is what is happening, that is k1 k2 Kn, this should be equal to Pn inverse. Okay, this is just a vector. This is just a vector of dimension 2 to the power n. So this should be equal to Pn plus 1 Kn minus 1 K1. So P inverse, if you take, so this should act as, this should also reverse the order. This Kn minus 1 Kn, this should also reverse the order and it will come back to this. So P inverse, so Pn inverse also does the same job at P to the power n, and Pn inverse is unique. So what we are saying is basically that P to the power n inverse should be actually equal to P to the power n. So this is one interesting property. So that is basically P to the power n, okay, square should be equal to identity. So we are basically looking for a particular set of matrices, unitary matrices or permutation matrices, whose square is identity. Okay, so inverse is itself. Okay, now we would like to use this property, for example, in order to construct, okay, what is, let's say, P to the power 3. Okay, so if I consider any three, let's say any three, let's say states, qubits, okay, let's say this is my psi 1, psi 2, psi 3. Okay, so what I want is that I want a matrix P to the power 3. If I apply this, this will change the order of the qubits. So if I write it, okay, so if I write it, so then what will be this one? So let's say I write it like entries are like let's say some a0 a1 times some b0 b1 times, or maybe I can just write a b c. There are three qubits, and this is c0 c1. So then what we have is, if I just multiply this 3 in the right hand side, so I will have 8-dimensional vectors. It will be, so I think you should know this definition. So let me just write it down. A naught b naught c naught, a naught b naught c1, a naught b naught c0, a naught b naught c1, then a1 b naught c0, a1 b naught c1, and a1 b1 c0, a1 b1 c1. Now so this is the vector representation of this. Okay, now what do I want? I want a matrix here, okay, such that if I multiply this one, if I multiply that matrix with this vector, okay, it should reverse the order of these entries. Okay, it should reverse the order of these entries. This is what it should do. So any idea how it can be done? What should be my P0? What should be this matrix?
8 cross 8 matrix with same like identity matrix, and first and last rows columns should be unchanged, and between second and last but one they should interchange columns so as to get that swap.
Okay. So what I want is, whatever the matrix is, doesn't matter, that should change. So if I multiply this, okay, this should give me this one, c0 c1 times b0 b1 times a0 a1. Okay, this should be the outcome. This is the output. Now see here, this will not change because this will be the first entry of this. So if we say that it is identity matrix only the first row will change. That will not be the case. So this is not going to change. First it. Okay, this is BJ. Okay. So yeah. So this vector is nothing but something like, so this, it has very special form. So this is C0, B0, A0, and so on. Okay. B0, B0, A1, so on. C1, B1, A1. So when I'm saying that it will reverse the entries, it is not exactly reversing the entries of this matrix, but you have to reverse some of the, you have to exchange some of the rows of this matrix, if you treat this vector as a matrix. Okay, so that it will ultimately reverse the ordering of these qubits. Okay, this could be a homework. This could be a homework. How to determine this. Okay, and so ultimately the question is, okay, we can find out for 2 for n equal to 3, but uh, I want to I want to find this my entries of this matrix when for arbitrary n, right? So I want basically p to the power n ij. I want that. Okay, let's say 1 is equal to ij is equal to the power for all the entries of this. So what should be the general purpose? So you can think about it. What is the ij? But let me just tell you that how can we construct a circuit corresponding to this matrix. From there it will be clear. So so let me just define this. What should be the matrix here, and then we can see why it is. And I will define this matrix, okay, in terms of swap gates. So what I'm saying is, when n is even, okay, then p to the power n, this will be equal to swap times swap times swap. This is n by 2 times identity order 2 by 2 times swap. We apply this rule, okay, whatever definition I'm giving for n equal to 3. I mean, I'll write down what is the case for odd and swap. This is nothing but you just have to observe what are those entries which are changing the order. Accordingly, you can find out that this is the case. Swap times I2 and then to the power n by 2. And here it is n by 2 minus 1. These are the swap gates. That means each of these, okay, is a matrix of order 4 by 4. Okay, so swap gate will do what? Swap rule AB was to be. This is how we define swap. And this one icon for this. I think I did not. I defined the icon like this. Okay, like this for the classical thing. For quantum, we will sometimes, or some people will denote it as like this. This is the swap for the quantum. Okay, and this is the relation also, you can say. This is a standard practice to write it this way. But when you are writing a circuit where there are some swap gates, so you write it this way. There are two qubits which are inputs, AB, and then you get B. This is the icon for the swap gate. Now if so this is for p to the power n when n is even, and if n is odd, okay. So I'm giving a factorization so that you can directly implement what is the circuit of this one corresponding to this p to the power n. This is identity times swap times swap times identity to the power n minus 1 by 2. This is n minus 1 by 2. This will be n minus 1 by 2 and whole times I2 times swap swap. Yeah, this will be also n minus 1 by 2. So you can check also if I suppose you take n equal to 4, okay, then there are 4 qubits. Now what is the corresponding? So if n is even, for example, here n is even, if you just write down, so there will be n by 2 here, there will be n by 2 minus 1, here it will be n by 2. If n equal to 4, then the circuit will look like this. So there are 4 qubits. Let's say these are psi 1, psi 2, psi 3, psi 4, and then there will be one circuit here. You can see that this is matching with whatever I say for even, and n is equal to even. Yeah, and then here you'll get psi 4, psi 3, psi 2. This is a circuit when n equal to 4, and similarly you have when n is odd. So like for example n equal to, let's say, 5, but we can see the change also in the circuits. So let us say 2, 3, 4, 5. So this is psi 1, this is psi 2, psi 3, psi 4, psi 5. Then you can see the difference, everything here. They're combining psi 1, psi 2. There too, you can see the change here. How psi 4 is going on the top. Okay. So there is an exchange here between psi 1, psi 2. Then there is an exchange here between psi 3 and psi 2. Then there is an exchange here psi 4 and psi 3. So 4 will go to this using this gate. Then we'll go to this, and then we'll go to this. We can see like how it is happening using this gate, this factorization, whatever I gave. So this is for n equal to 5. Then there will be psi 1, psi 3, and there will be here psi 3, psi 4, yeah, psi 4, psi 5. Similarly, there will be here, there will be here once. From circuit, you can see how it is happening. So this will give psi 5, psi 4, Okay, so you can just check and see that this is what is going to happen. Like you can realize reversal permutations. Okay. So this permutation matrix will be used in quantum Fourier transform. Okay, now before I start quantum Fourier transform, we have to understand. I'll just recall what is the basic definition of Fourier transform. Like it is, uh, you had a course, I think, transform calculus. Okay, so what do we talk about there? Fourier analysis or Fourier transform or Fourier series. So what happens is, so what is the meaning of Fourier transform? And then we'll say, okay, if how do I define Fourier transform when I have n input as n qubits? So why this n is coming here? How the n is coming here? So what is happening in Fourier analysis? What happens is, so this is the famous idea, but this EC people or E people will use that this is kind of a periodic signal. Okay, periodic signal. So signal is not mathematically, it is just a function, and there is a pattern. Okay, from some L to minus L, you can write it like that way. So and there will be some pattern which is, let's say this pattern is, it's something like that. I mean, it could be anything. Okay, something is repeated. So let's say this is repeated over entire this entire submitted. So this is a bit of it which is repeated. Okay, so this Fourier transform. Okay, what does it do? So it converts a periodic signal from its time domain to frequency domain. What is the meaning of time domain? So whenever, so you are treating this as a signal, let's say this is a function. So this x-axis is, let's say, time, which is, let's say, t. Okay, so now what happens is when it says time domain, let's say, so time domain. Okay, so in order to describe the signal, okay, now to monitor the signal, what happens is this is an infinite set. Okay, this entire interval. But in real life, you cannot realize. So whenever you have a signal, you cannot realize this for all possible times, right? So you have to consider finite sample points, finite time, and then you will get the corresponding values here. Okay, this is how a signal can be realized. Okay, so I can say, just say it is a, when I say time domain, it means some values, some data, okay, that vary with time. Okay, so it can be considered as a time series data also. Okay, this is time domain. So this is a function which has some values depending on the time, and the time is finite. Let's, we can also call infinite in general when we are talking about, let's say, analog signal as a kind of a thing. You can talk about that. Okay, this is the piece of thing. But ultimately, when you do it, time is finite. Some sample points we can say. But in general, you can say, okay, this is a, if you want to define it as a function, so sometimes you will say continuous time signal, discrete time signal. So time is continuous, time is discrete. Discrete means it is finite, and some particular points, okay, on the time domain. So it will convert this periodic signal from time domain to something called a frequency domain. Okay. So what is this domain here? So I mean, what is the what is the corresponding signal here? Frequency domain means it is also a sequence of data values. Okay. But here this data, okay, this data, they represent the contribution of different frequency components which is there within the piece, within the signal. Okay, so here time domain, and here there will be frequency. Okay, how much frequency? So here let's say frequency. There is a term, I think, in quantum, sorry, in Fourier, in transfer calculus they use, this is time and this is omega or something. That's how they write it. Okay, so okay, so this is only thing we need to know. But the thing is, what is happening is, that whenever you have a periodic thing, so I'm not discussing anything like okay very precisely. Everything is precisely okay. So I'm just giving an informal introduction because you already know all these things and you have used this Fourier transform tool to solve some kind of OD, PD, and so on. So what is happening is if you have a function t, let's say this is periodic, okay, then you always say this is called what is called a Fourier series. Okay. So this always can be written as a zero by some constant, and then so in terms of a linear combination of some sine and cosine function, and this n and bn and a not, they can be obtained using some formula. What it means is basically since this is a function and you have a vector space, okay, of all functions, let's say, okay, or periodic functions with some additional conditions, such that using that condition we can calculate this integration. So this has to be integrable first of all. All those functions, and all those functions where I can perform this integration. So this is the same thing as like what we are doing for like the quantum. Same thing because this is also a linear combination of these functions. This is cosine, sine. This is another function, and n is varying here. Okay, and this is the function. Let's say constant function which is one. So here their orthogonal basis or orthonormal basis is like 1 cos n pi by t by L and sine n pi by t by L. So it's nothing but a linear combination. Okay, but this is infinite because this basis is infinite. N belongs to it's a 1 2 up to okay, 1 2 up to infinity. Okay, n belongs to natural linear. Let's say. So this set is an orthogonal basis for a vector space. Then using the inner product, and this is the inner product. Using this integration, so using the inner product, I can get these values in n0 and b, and this is orthogonal to this one. I can check that in that domain. So it is let's say minus L2. This is the domain. So using that, so this domain is minus L2. Let's say. So using that, we can have this. So this is basically the thing about Fourier series. So what it says is basically it doesn't matter okay how your signal look like, the periodic function here look like, okay, it can always be approximate. So this is an approximation basically. So this can always be approximated using some combination of sine and cos and this is periodic signal. That means it need not be like a differential function also. It is just kind of any periodic function. Okay, maybe its derivative will be something. Okay, a derivative need not be. Here these are all smooth function. Smooth function means this function like anytime how many times you want to calculate derivative you can do that and so on. Okay, so these are very nice functions. So using these nice functions you can approximate any function. Okay, this is what the message is using Fourier series. Okay, now what is a so yeah, so now what is a called um, yeah Fourier transform. Okay, so or something called a discrete Fourier transform. So as I said before that even if you have a continuous signals, but when you monitor this using some kind of a machine or anything, so you always have time which is discrete. Okay, so that means in your time you'll get some values of this time. Okay, and so you'll get some, let's say the function like this. Okay, let me just write like this one. Okay, so then you can say like approximately your function looks like this. Okay, so yeah, so it is nothing but the same thing, but here you have finite many sample points. Okay, so and these are the measurement that is. So this is where you measure these values. Okay, this is your time. So there is a time gap. Let's say it is delta t, and there is a number of points here, which is let's say n. So I can say like whenever j delta t, okay, j equal to 0, 1, 2, up to dot, dot, whatever the number of this function. So if you have 1 to n points, like suppose there are n capital N number of points, then delta t okay, is approximately then, because you want that to happen. So this T sum are the T max and this T min, let's say. Okay, so you want to have n observations. So this will be some T max minus T min by n minus 1. Okay, because there is n minus 1, because there is an point in the end and one point in the beginning. So these are like the gap, like j equal to 0 starts from 0 here. Okay, then j equal to 1, so it is delta t, then j equal to 2, then there will be 2 delta t, then 3 delta t, 4 delta t, and so on, and n minus 1 delta t. So at different points, these values. Okay, can you see the screen?
Yes, sir.
Okay, so what is happening here is when you take discrete Fourier transform, or basically you discrete the discretization of the
Sir, screen went
matrix
off.
P.
Screen went off.
Okay, just can you see the screen now?
No, sir. No, sir.
And then you can see it moving.
Yes, sir. Now it's visible.
Yeah, so what is happening here? So if this is my f, this is my f, you can this is the continuous time signal. Then when I take the discrete version of this, then I know the values of this f, okay, at some specific point in the time domain. So basically, I do not know the entire continuous function. Rather, I know ft, okay, which is defined by a set of points, which is equivalently saying I know this set of points f0, f of 1 delta t, f of 2 delta t, and f of n minus 1 delta t. These values I get about the signal. So these values I know, these values I know, and then from there I want to reconstruct. So this is one way to do it, but you can have other ways to do. You can have other ways to do it also. Let's say I want it like this way. Okay, okay. This can also be empty, right? So I don't know. So basically, the thing is, from this finitely many values, I want to reconstruct my empty. Okay, and all you know, like this finitely many points. But there, so I'm not going into that. But there is, then the question is, how many points are good enough? Like this points, how many number of points you should know the function values so that you can reconstruct the original signal. And there is a criteria for this. I think it is not done. It is a transform with a transform calculus course. So this criteria is called Nyquist criteria. Okay, if it satisfies that, then this can be this function can be, this origin signal can be recreated or reconstructed. Okay, so basically this says that if ft does not contain any frequencies greater than or equal to some omega, okay, or omega hertz, whatever you say, okay, it is completely determined from the knowledge of its samples at every time, at samples at times, okay, 1 by 2 omega seconds apart. That means there is a gap is 1 by 2 omega if the signal does not contain, okay, this omega frequency, and frequencies, okay, not greater than omega seconds apart. Then this always can be reconstructed. So there is a way. So you already know. So there is a proof for this, but anyway, we're not discussing that here. So then there is a criteria like how many sample points should be at how many times you should know the function values in order to reconstruct the continuous version of the signal. Okay, so this is more. Now how quantum is coming here into the picture. Now the discrete, if you have understood like the discrete Fourier transform, okay, so this is like, so basically the idea here is this is nothing but the information you have, this set of points f0, f1, f1t, f2 delta t, and dot 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 fn minus 1 delta t. So there are n points, n values, capital N here, okay? Capital N values. These are given to you. So this is a set of numbers, okay, you can say complex numbers also. So these numbers are given to you and you want to uh, take a transform of this in order to get something in the frequency domain. So this is the time domain. We want to get something in the frequency domain. Okay. So this is what is called, something called a DFT. So DFT basically, I mean the discrete Fourier transform with the classical case, it will be nothing but a matrix, which will be again a unitary matrix because it can be transformed from time domain to frequency, and it can be also, you can also should get back from frequency to time. So this function has to be invertible and it should also preserve the length. Okay, so it can be realized by, or you can just, okay, I'll talk about that also. What is discrete Fourier transform, that matrix, when I'll talk about the quantum version of that, I mean QFT, quantum Fourier transform. So what the quantum, why the quantum is coming into the picture here. Now these values somehow you can associate, okay, the sample points, we can say this can be associated with a state, a quantum state, okay, of n qubit system. This n is this capital N qubit system. Okay, so now the thing is, using these values, I will define a quantum state, and then I'll take the quantum Fourier transform, or just the Fourier transform of that quantum state, and then that transformation, that matrix, will be called as quantum Fourier transform. So first, I need to associate a quantum state with these complex numbers, set of complex numbers. So how can I do that? The simple, the obvious way of doing it is that I can define a function every time. Sorry, I can define a state. Okay, let me write it as the signal. The signal corresponds to this. This is my state. Okay, is since these are complex numbers, I will use some qubits, n qubits. Okay, and take the linear combination of those n qubits, and these n qubits are nothing but, let's say, they are the basis, standard basis elements, and then I will take the linear combination using these as the coefficients. So what I'll do here is, so how I'm constructing this quantum state, it is like f0 0 plus f of 1 delta t 1 plus f of 2 delta t 2. I keep on doing that, f of n minus 1 delta t and then n minus 1. So basically I have constructed a quantum state, so which is like this, is a linear combination of this standard uh, basis vectors. Now the thing is, if capital N is anything, okay, I want to do that using this as n qubit system. Okay, so I want this capital N to be like 2 to the power n, something like 2 to the power n. So I want to realize this state in terms of an n qubit system. So I want this capital N to be 2 to the power n in this particular form. If you have something like a complex, something like a prime number like n equal to 5, then what will be my how many qubits I will require, that will not be able to understand because I will not be able to construct that. So this is the first step which you learn for quantum algorithms, is that in a quantum algorithm, whenever there is an input and your input is n qubit, that means, so for example, if it is a search algorithm, okay, the number of data points you are given to you, like for example, you are working with Excel sheet, okay, you want to search a, let's say, a sheet, with the Excel sheet there are roll numbers, but okay, roll numbers correspond to each row, okay, and this roll numbers is not structured, meaning it is arbitrarily put, okay. Now you want to search a particular roll number, so that means you want to search means you want to know the row number, which row contains the desired roll number, okay. So then when you are considering, when you are converting this problem into a quantum algorithm, then you also always have to choose this number of row numbers, number of points in that sheet, Excel sheet, is 2 to the power small n, because otherwise you cannot have a quantum state or which can be represented as n qubit. So here we are always assuming this number of sample points, capital N, is of the form 2 to the power n, and then only we can have a quantum state. Although it need not be a quantum state, by the way, because it need not be normalized, because this could be any values. This could be any values. This need not be this need not be a quantum state. It is just a vector now, right now. Okay. So if I want to make the quantum state, okay, so then I have to normalize this. Normalize means I have to divide this vector by its norm. Okay. So what is the norm of this? Because these are the basis elements here. So norm of this. So I want this to happen, right? So mod of f of, let's say, j del t square, j equal to 0 to n minus 1, this should be equal to 1. But if it does not 1, I'll normalize this term here for each of this, and then I can construct this, okay, this quantum state. So my actually required signal is, or the desired signal is, or the input or the representation of quantum state corresponding to those values is nothing but sum of j equal to 0 with capital N. So capital N is nothing but 2 to the power n, is f of j delta t divided by square root of sum of, I can write j here, so L equal to 0 minus 1 f of L delta t square of that, and then j. Now this is a quantum state, okay. Now I want to do what? I want to define a matrix which I'll call it a quantum transform. So I want to define a particular matrix, let's say Q, or let's say QFT, which I want to apply on this, and I want something here, okay, some desired output here, okay, which, let's say, this desired output is nothing but the, if I replace this by DFT, and if I replace this by the classical, the vector, okay, which is formed by the entries of the vector should the these values, f of these values, then that should do the same job. Now I'm bringing that into quantum. You know why I'm doing that? So here there could be exponentially many points, Okay, here. What is I'm talking about what is the advantage of bringing everything in the quantum domain, not doing the same thing in the classical domain. So here, how many points I have? 2 to the power n. Okay. Then classically, what have is I have to construct a matrix DFT of order 2 to the power by 2 to the power n times 2 to the power n, and then I have to make a matrix vector multiplication. But when n is large, this could be a huge thing to do. Okay. This is not classically possible for all large n. But what happens if I bring that thing into quantum domain, will show that this circuit corresponding to this matrix QFT, okay, needs only polynomial number of uh, polynomial size n, okay, polynomial of n size, I mean size of the circuit, the number of gates of the circuit, okay, or number of operations you can also say, because the number of gates will be nothing but operations. So that could be polynomial in n. In n is nothing but this 2 to the power, this same n, small n, let's say, small n, small n here. Okay, so in terms of polynomial of the small n, so in polynomial operation of this can be constructed, it can be realized, this quantum Fourier transform. So that's why I want to bring it in the continuous in the quantum domain. Okay, now I want to have this desired this thing, but so when I'm defining this quantum Fourier transform on this size signal on this vector, so it is enough to define this QFT on this individual computational basis. So if I define QFT, because it is a matrix, if I know, let me write it as 2 to the power n, because then I will clear how many points are there. This is up 2 to the power n. Here is the dimension of the state. Okay, so if I apply, if I know this, okay, then I'll know what is this. Okay, so let me define what is the role of this, how does it transform the action of this QFT on a particular basis state. Okay, so then I am defining it this way: 1 by square root of 2 to the power n sum over k equal to 0 to 2 to the power n minus 1 e to the power 2 pi I j k by 2 to the power n and then k here. So this QFT to the one, this is a matrix acting on a computational basis element j. So j could be from 0 to 2 to the power n minus 1. Okay, well, capital N is 2 to the power small n minus 1. And then here you have a scalar. Then you will get this a linear combination again of the basis states k. The k is from 0 to 2 to the power n minus 1. So this is how we are defining, and you will see the QFT. This is the definition of QFT, and you will see that this QFT will be used in order to in different kinds of algorithm. Maybe we'll talk about that later. But like the phase estimation algorithm, eigenvalue estimation algorithm. So this is one of the fundamental tools in quantum algorithm, where in most of the big algorithms, people will use this QFT because it can be implemented using polynomial number of operations. Okay, so that's why it is very good. So you can have exponential speed due to this quantum Fourier transform. So instead of a very large matrix, classical 2 to the power n by 2 to the power n, here you'll have a very small size matrix as a polynomial. Okay, we'll talk about that. Yeah. Okay. Now the question is, I want to realize uh, this, how it acts on this. Okay. Then the question is, if this is how it is defined, the QFT, then what is this? This is just a state. For example, I can ask, okay, is this state is entangled state or it is a separable state? What kind of state is this? Because this is the state, the output state is written just as a linear combination of the fundamental states. But I want to know what is this state. In fact, when I want to create a circuit, how do I realize this? Because the circuit for this, so that should, okay, give this as the output corresponding to the input, which is a fundamental basis element. So I need to know what is this. I need to do some calculation to understand a computational meaning of this cubic of the state in the right hand side. Okay. For that, I have to develop some machinery. Okay, so I need to understand something. Let me discuss that. Now here, this what is this J? J could be J could be values, okay, from 0, 1, dot, 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 to the power n. So basically, this is an integer. This is an index integer, right? Index integer. So this is an integer in the decimal system. Okay, this is an integer in decimal system. Okay, let me write it as J10. This is not decimal system as an integer. Then this integer will always have a binary representation, right? Which is, let's say, J1, J2, dot, 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 some J, because it is up to a order to the power n, there will be n such 0 ones. So this is a binary representation of J. So if this is the binary representation, then actually if you convert this binary to decimal, then this representation is nothing but 2 to the power n minus 1 J1 plus 2 to the power n minus 2 J2 plus 2 to the power 0 Jn. So this is the corresponding decimal. So if that is the case, then I can say this is nothing but 2 to the power n to the minus 1 J1 plus 2 to the power minus 2 J2 plus dot dot dash 2 to the power minus n Jn in 10 in decimal. And this is same as saying 2 to the power n point or 0 point J1 J2 Jn in the binary representation. Okay, this is the binary. I will use this conversion from here to here. I'll use this conversion in order to understand what is this right hand side, because there is a J here. This J is same as this J, the left hand side. So this J is same as this J. Okay, so this J is an integer. So I want to use its representation like this, whatever we derived here, we want to use that. Okay, so let us see what is the right hand side of this QFT. So let me write it. So then what is happening here is QFT to the power n J is 1 by square root of 2 to the power n sum over k equal to 0 to the power n minus 1 equal to 2 pi I jk by 2 to the power n k. Now this we can write as the following. This is equal to 1 by 2 to the power n, and this k is again an integer, so k will have a binary or k, we can just write this k as a kth, so it is nothing but a basis element, so we can write this k as some k1 k2 dot dot kn, because it is n cubic. Okay, this k, it is the basis element, right? So it is of this form k1 k2 dot dot kn, because it is 2 to the power n minus 1. I mean 0 to 2 to the power n minus 1, k is from 0 to up to 2 to the power n. So this is the basis 0 1 dot 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 up to 2 to the power n minus 1. So this is the basis for c to the power 2, so n qubit space. Okay, c to the power 2. So this is n times, or it is same thing as says c square times n. This is also notation. Okay, so this k, I want to write it in terms of this n qubit notation. Then this I can convert it, because the k is like that, k1 k2 dot dot kn. I can write it 2 pi I j. So k can be written as this, sum over some L equal to 1 to n kl 2 to the power minus L. Okay, this always can be written, okay, for any k, because of this. Okay, so, or you can say because of this. So, and then here, then I can write that k1 or maybe kn is from 0 to 1 dot dot dot, k2 is from 0 to 1 dot k1 from 0 to 1. So then this becomes ultimately 1 by square root of to the power n sum over k1 equal to 0 to 1, k2 is equal to 0 to 1 dot 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 sum of kn equal to 0 to 1. And then this can be written as a product because I want to then split this out. So in terms of kn, k2, kn with the power 2 pi I j kl to the power minus l kl. Now this here is, again I can write this in the inside the product. So it will be 1 by square root of 2n. Take the product l equal to 1 to n summation kl equal to 0 to 1 e to the power 2 pi I j kl to the power minus l kl. And then this is a straightforward calculation. Square root to the power n l equal to 1 to n. Now if I write kl to be 0 or 1, you can see that this is either 0, okay, plus 0 is 1 plus e to the power 2 pi I j to the power minus l 1. So now I will write what is the meaning of j. So this to the power n. So now I can write this as to the power n 0 plus e to the power 2 pi I 0 dot jn. So this j, now I'm using this representation, this one, jn 1 times 0 plus e to the power 2 pi I 0 dot, so 0 point basically here, jn minus 1 jn then 1 dot dot 0 plus e to the power 2 pi I 0 point j1 j2 jn 1. So this is the product of all these n qubits or all the states, qubit states, which are of this particular form. So from this manipulation, algebraic manipulation, we already know that the right hand side, so the output of this QFT on J, this is the product state. This is the product of this qubits. So this is not entangled. This is separable. This is a separable state. Separable state. Okay. So then what happens is, after this calculation, we can directly write what is the effect of this QFT on the entire signal. So this is just the QFT on J. Okay. And then we can write what is the effect of QFT on the entire this thing, on the entire signal. Okay. So this is my definition for the QFT now. So psi signal, the original signal. Okay. If you do a QFT, so it will give you this. So this is just a mathematical definition, but in a quantum domain. But we have seen that this has this kind of a, this case is the output. So whenever we are constructing a circuit representation of this unitary matrix corresponding to the QFT, then the output must be, so if there are n inputs, okay, this is the standard, let's say inputs, n inputs, then the output must be of this particular form. Like one should be this state, another one should be this one, and dot dot dot, and another will be this one. Okay, so this should be the output state. So this is what we wanted to realize. That's why we have done this algebraic manipulation. So otherwise it is just a mathematical definition, which is k equal to 0 to this to the power minus 1, then j is equal to the power n minus 1 f of j delta t to the power 2 pi I jk by 2 to the power n k, assuming that this is all normalized. Okay, so this is the QFT. And then the question will be, how do you implement this? So this QFT has important applications in exponential speed up in, for example, source algorithm. Okay, so this is used in, for example, all the famous algorithms like Peter source algorithms. So this is called prime factorization problem, or just the factorization problem algorithm. Okay, and phase detection. So you can see here how the state, this is different from this one. This is only here, only the phase factor is different. Okay, only the phase factors are different, otherwise everything is same. So also this is used in phase detection. Phase detection means what? Suppose we have a qubit, let's say. So this is alpha plus 0 plus beta 1. But we said if we do measurement, we don't know anything about alpha and beta. But it can again we have a nice representation in terms of 3 parameters. So this is plus sine theta by 2 to the power I5. Okay, 1. So we don't know nothing about this, but can we approximate this value? The phase factor is the relative. This is also called the relative. Can we detect this phi? Okay, so for phase detection this is used, and then of course eigenvalue estimation problem. Eigenvalue for, let's say, unitary matrix. Okay, eigenvalue of unitary matrix. Eigenvalue estimation. So in this things, this QFT, quantum Fourier transform, is used. Now, so let us recall what is okay. So if this is the case, so this is just a vector, right? This is just a vector. So we can realize this by unitary matrix. So let me just write down what is the matrix representation of QFT. So whatever we have done here is everything actually very simple, although the notations are very, very complicated. So the QFT, if you write it, QFT will be the matrix representation of this is nothing but this 1 1 all 1 all 1 1 all 1, and there here it is W1. You can see the pattern. Let's say 1, and this is 2, or this is omega, not W, but 2 to the power n minus 1. This is omega square. This is omega 4. This is omega 2 to the power n minus 1. So on omega to the power n minus 1, omega to the power n minus 1 by 2, and omega to the power n minus 1 to the power n minus 1. So basically this is the matrix. What is the ijth entry? So let us label this as 1 0 0 1 2 dot 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 up to the power n minus 1, and the columns also like 0 0 0 1 2 to the power n minus 1, and the ijth entries, okay, the ijth entries, so is nothing but ijth entry is nothing but 1 by square root of 2 to the power n omega to the power jk. J is the row and k is the column number. So this jk are from 0 to up to 2 to the power n minus 1. And what is omega? Omega is this 2 to the power nth root of unity. So omega is e to the power 2 pi I by capital N, means 2 to the power n. Okay, yeah, and the I is of course square root of course. So this is the matrix. Now the thing is, say here, there are two things. So a physicist, okay, they use this, they choose this omega to be equal to class of this, meaning this one, this precisely this one. But electrical engineers, they prefer this omega to be equal, because this is also is classical. This is minus. Same thing means you'll get a different matrix. Okay, but this is also square. This 2 to the power n unit. So yeah, so this is preference for electrical engineers. Preference for electrical engineers, and this is for physicists. Now, what is the connection between this corresponding matrices? I mean, if you choose omega to be equal to this and omega to be equal to this, so if you take omega to be equal to this, and then you construct this QFT, then you take an inverse. The inverse will be corresponding to this omega, corresponding to this omega. So whatever is quantum Fourier transform for physicists, that is inverse quantum Fourier transform for electrical engineers, and whatever quantum Fourier transform is for the electrical engineers, that is actually the inverse quantum Fourier transform corresponding to this, because this matrix is unitary. So question will be what is its inverse, and then you will see the inverse is nothing but if you replace this omega here by minus here, the omega bar here basically, so then that will be the inverse actually. Okay, so once you have quantum Fourier transform, you can also define what is called uh, unitary, this inverse quantum Fourier transform. Now, question is now, how do we implement this? What is the quantum circuit for this kind of a mm, representation? So, what is the representation? I want whenever my input is this j, so this j is n qubit. Okay, this j is n qubit. So I want this to be the output. So this is the product of this. So what I want to basically do is whenever I have j, which is like let's say j1, so whenever this j is nothing but let's say, as we said, the binary representation is j1, j2, jn, let's say. So if these are the inputs, okay, I want to use some gates here in the circuit such that finally I want this to be equal to, okay, in terms of this, okay, for all j in terms of this. So this can be written as this one, so this k, so you can say k1 k2 dot 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 up to the power 1 minus 1. Yeah, so yeah, in terms of this k, so I will have n k qubits, such qubits. So if k equal to, let's say, if k equal to k1 k2 kn, then I want this to be finally k1 k2 dot dot dot. Okay, this is what I want. Okay, now how should we implement this, and what are the gates corresponding to this? So here this will use basically two gates. One is Hadamard gate, square root of 1 1 1 minus 1, and another is the phase gate, but this phase is with particular value. Let's say, let me define this Rn, which is 1 0 0. Why it is? Because if I apply this gate on a qubit, it will change its phase, local phase, or the relative phase. I multiply this with some psi, and we have seen that, right? This is done with the RZ gate with this particular delta by 2. So then this will change the corresponding this thing, okay, the relative phase. So yeah, this is okay. Let me just draw the circuits, okay, and then you'll see why. So let me write in the circuit here. This is H, and this will be, okay, my space is very small here. So dot 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 Rn minus 1 Rn, and this is controlled by this. I need to draw one more. So this will be controlled by this one. This will be controlled by this one. Then I'll have the same thing here for J2, and then dot dot dot. I'll go up to Rn minus 2, and then Rn minus 1. So this is controlled over this. So there are other qubits here. This. And finally, I will have H here, and then Rn here. Rn controlled on this. And finally, I will have a Hadamard gate. And finally, here, I'll use this permutation gate. And then I'll see, I'll get K1, K2, K. So this is a circuit. And I will not explain why I'll get the desired output, but you can just analyze the circuit and check why we'll get this. Just understand the one thing you have to just understand, that this will give me the effect of a change in the relative phase of the output. Yeah, so this will do the job, and this is the quantum circuit for this. That is called the quantum Fourier transform. Okay. Yeah.
Sir, that
Any question?
permutation rule, can you like just tell why it comes here?
What is that?
Permutation at the end, permutation matrix comes, right?
Yeah.
So, why like
Okay.
that
So
swaps, that P swapping matrix only, right? Like swap, which we discussed earlier. Hmm. Hello, sir. Sir, you are muted, sir. Sir, you are muted, sir. Sir, you are muted. Sir, you are on mute, sir. Sir, you are on mute, sir. Sir, you are on mute. Like we can't hear you. Sir, uh, sir, you are on mute, sir. Hello, sir. Hello. Ah, sir, you are on mute. Sir, you are on mute, sir.
okay. Oh, I did not understand. I was
Um,
okay. So let me repeat it again then. So what is happening? Oh, so if you do not apply p to the power 2n, what will happen is this k1 will be actually kn. So because you are applying this so many n r2, r3 dot 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 up to rn. So this basically this output correspond to the j1. If you do not apply p to the power n, then it will be this one, the last one, because the corresponding changes here in the relative phase, you will see J1, J2, 0.J1, 0.J2, I mean J1, J2, Jn. So that's why you are actually applying this thing here, R2, R3, this Rn. And similarly here for the J2, you will see that the next second last one will come. I said this is a good question. So this is the second last one will come here. So this will reverse actually, but you want to have this kind of a thing. So this will be the first output. This is the second one, and so on. So that's why you are applying this. So if you want to do, if you do not want to apply this permutation gate, what you have to do is, I said this has to become, this has to come here, this has to come here, and so on. So you can design your circuit if you want to avoid to use the permutation gate. But here we discuss about this permutation to the power n, because I also wanted to show you that there is an importance about permutation gates as well, which you have also in classical computation. this permutation matrices. So you can actually, so this could be homework. What is the DFT? This is QFT. Now we can check out what is the DFT. So we did nothing, basically nothing new. We did nothing new. So this is just a little bit of calculation here. And this calculation is also, this is, I would say, the tricky calculation. This is very clever calculation. There is no innovation in, I mean, there is no very big discovery in this calculation. Okay, but this is nice. And then we converted this classical problem. So the homework is just find out what is DFT, the discrete Fourier transform, what is the matrix, and this is the QFT matrix, quantum Fourier transform. See what is the change here, and this 2 to the power n by 2 to the power n matrix. Okay, this is huge order matrix. This can be realized using only polynomial number of gates here. So this is the most interesting part. So you are getting exponential speed here when you are implementing this QFT. So that is the advantage. And only trick is this one. This taking the Fourier, taking the decimal to binary. This one. Only trick is this one, which you are using at the last. Here also you have using the K, but here, so basically this one. Yeah. Yeah.
And Hadamard is to make into all the bases, no sir, the H gate.
Yeah,
So,
say you need here. So here you see why do you need a Hadamard? Say J1, J2, these are all 0 or 1, right? J1 could be equal to, let's say,
yes.
0, J2. But you want to make it to of this kind of a thing, 0 plus 1, right? And then you want to change the phase. Here you
Yes.
see, says, yeah. So, yeah. So whenever you have this H, okay, the Hadamard gate, you already have a quantum, this linear combination of 0 and 1. So then you are applying Rn because you want to now change the relative phase, because ultimately your idea is to obtain this right hand side one, which is a product of a tensor product of this corresponding qubits, and the change is only in the relative phases. That's it. And so this is a yeah. So this is a very important tool which is used in all the famous algorithms to achieve an exponential speed. Yeah. Because what I usually do not do it in the beginning, but this time I think I'll not be able to discuss many algorithms. But so if this is known as a tool, then you can yourself read some algorithms and you will understand what is the use of this. Yeah.
Sir, what was DFT, sir? Like DFT in terms of quantum.
No.
The,
This CFT in terms of quantum we discuss quantum Fourier transform. This is just a discrete. This is classical.
okay,
Whatever
okay.
Fourier transform you know, so that classical, but this is also called discrete Fourier transform. What is that? Discrete Fourier transform. This is a classical. So what you can do is you can just see what is the difference between the matrix representation of the discrete Fourier transform and the matrix representation of the quantum Fourier transform. You actually see the same thing. So same matrix, there is no change. Okay, because we are realizing this discrete Fourier transform using quantum. This is the most important part. So how we are realizing it, this is here. But the matrix has to be same because it is doing the same job. The quantum Fourier transform is used to realize this discrete Fourier transform. The advantage very huge. The advantage is exponential speed. Okay, so that's why I just asked you to look into that. Yeah, so I should not say this is the exactly same, but just see, just check what is that, is the same or not. Let's say. But the question is that where we are calling it quantum Fourier transform. There is already the classical Fourier. Is it the same thing or not? Same thing means, is it the same classical transform you want to implement it in a quantum platform or not? That's the question. So that's why I said, okay, just find out what is the matrix, then you will see what is that. Yeah.
Okay, sir, got it.
Okay. Okay, anything else? Oh, I did not stop the recording.